Welcome back to E555 again. Let's try to wrap up the overview set of charts before I give you some review on queuing theory. We started looking at, this is all material, by the way, this is all material from quick review from 450. You have seen it before, but I just want to refresh your memory. We started looking at internet organization, and we said that the internet organization consists of several types of networks, the customer networks. In the customer networks, we see a whole bunch of hosts, hubs, routers, local area networks, and so on and so forth. Mostly, it's a local area network type customer networks, local area network. And then we have a series of ISPs, the internet service providers, and the internet service providers network consisting of several routers and point of presence. Remember, point of presence, these are what? Switches where traffic is going to be collected, traffic from several customers going to be collected and exchanged. We call it POP. POP is the point of presence. Every service provider has several POPs all over the place, and we will see that in just a second. So, and then those POPs are interconnected via what is known as the backbone operator or the core. We refer to it as the core network. Core network, and in the core network we see again a whole bunch of routers, whole bunch of switches, POPs, and links, and so on and so forth. The backbone operators, or the point of presence here, are also may be connected to what is known as network access points. I will show you that in just a second. Network access points. So if you see a diagram in here, for example, this is a customer network. All of these are customer networks interconnected to a what? To a point of presence. The ISP, the service provider, collect the traffic from all of them. This is the access network that we referred to last time. It's going to collect the traffic from all of them. And then the ISPs are connected to the what? To the backbone service provider. Those are the big networks. The backbone service providers are the big networks through what? Through the, again, through POPs, the point of presence. Now, if you notice, the backbone service providers are either connected directly, as we'll see shortly, or they are connected via a third entity, which is referred to as what? The NAP. The NAP is the network access point, network access point. Through this NAP, they are going to exchange traffic among themselves. These are different backbone service providers. Could be, for example, AT&T, could be Verizon, Sprint, and so on and so forth. They are still interconnected together via those NAPs. And we'll see what goes inside the NAP in just a second. So it's a hierarchical structure. Now, if you look at the hierarchy of the internet based on the routing, again, we have seen this from 450. We divided the internet into what is known as, anybody remember what AS stands for? Autonomous. AS stands for, written here, autonomous systems. And autonomous systems is a system under a certain organization. One organization that controls the administration, the management of the network, and so on and so on. So this is an autonomous system, this is an autonomous system, autonomous systems, and so on and so forth. Routing within the autonomous system is what is referred to as what? domain routing. Inter-domain routing is within autonomous system. Let's see if you remember examples of this is, for example, RIP. RIP stands for what? The Routing Information Protocol. Another example is what? Is the OSPF, the Open Shortest Path First. This we will not study in this semester. We already have studied them in EE Perfect. What we are going to be studying in detail in this semester, which is the more challenging subject, is routing between the autonomous system. How do we forward the packets between the autonomous system? In here, we use what is known as the inter-domain routing. And in this case, we will study what is known as the BGP. BGP stands for the Border Gateway Protocol. This is a very complex protocol, but we will spend time trying to understand how it works, and you will also study it in CS 551. Anybody who has taken or is taking CS 551, we will study also the BGP. But in our course, I cannot guarantee everybody will take CS 551, so I will introduce you in some detail into the Border Gateway Protocol. The reason that this one is more complicated than these is that because this one has to play by the rules of the policies or rules or policies of each autonomous system. These are separate autonomous systems. Maybe this autonomous system does not want packet to come from what? To come from this autonomous system directly to it. Depending on the policy, depending on their rules, every company or every autonomous systems have their own rules. So we will see all the aspects in this one here. And I will ask you also as an extra credit assignment to analyze and simulate this protocol to understand it a little bit better. From a functional, we already talked about this last time, from a functional organization point of view, the internet is divided into three types, which is the what? Which is the access network, the router core, and the ATM or the SONET core. Now, this one is evolving. Again, this one here is evolving into the dense wavelength division multiplexing. So we will see that how is this one is changing. Clear? The router core is the metropolitan area network, the metro network. All of these are what? Are high-speed routers in here. And we will study the structure or the architecture of these routers shortly. The access network, we studied them last time, consisting of, for example, ADSL, cable access, a fiber to the home, or the passive optical networks, and so on and so forth. All of these are referred to as the access networks. We already talked about this last time. This is, for example, an example of a large ISP network, Internet Service Provider. These are all customers connected to ADSL. They are going to carry the traffic, all of them carry the traffic and give it to the what? Give it to the POP. Remember from port 50, we divided the internet into what is known as tiers. Tier 1, Tier 2, Tier 3, and so on and so forth. Tier 1 is the backbone, which is the core network, which is the largest or the fastest network that can carry the traffic from multiple users. These are the metro networks, and you can see that the metro networks are also connected via what? The other metro networks, and so on and so forth. The connectivity between, let's look at, before we get to this, look at this. Here we have an ISP, another ISP. They are either connected via what? Peering means what? Peering means equal. Those ISPs in this diagram, if you see them, which diagram? Let me show you here in this diagram. You see this ISP is connected to this ISP-C directly. Clear? Via points B, for example. Whereas in this case here, they are connected via what? Via an app, the network access points here. So they are either connected directly, we call it what? Private peering. If this peering, either what? Private peering. In a private peering, they say what? They say to each other, those the high tiers network. Each one tells the other one, I will carry your traffic if you carry what? If you carry my traffic. Private peering or what? Or via what? Via NAP. Via these points. By the way, an ISP could be connected to multiple NAPs. So this one here, for example, NAPs, it's another NAPs, and so on and so forth. Dual homing, ISP can connect it to what? Can connect it in a peer type, or it can connect it to an app. We call it what? A dual homing. ISP-C is a backup provider for both A and B. This A and B, for example, is connected to what? ISP-C, ISP-A. This B is connected to ISP-B, ISP-C. So a customer network, for example, could be connected to multiple ISPs rather than just a single ISP. In the NAP, this is what you see in the NAP. In the NAP is a high-speed LAN. This is coming from what? Coming from different ISPs to the POPs. These are, the ISPs connected to high-speed routers, and the routers are attached to a high-speed local network. Most of the time, it's a gigabit Ethernet or 10 gigabit Ethernet currently, or ATM switch, high-speed ATM switch. It is at this point they are going to exchange traffic from this ISP to this ISP to this ISP, and so on. So this is an app, the network access point. And again, we will study in detail the architecture of these switches, high-speed switches, the interconnect the several ISPs. And again, as I told you, ISPs can be interconnected to either direct peering, or it could be connected through the NAP. All of these, again, we have seen them in 450. Now, internet fallacies. Fallacies means what? Myth. The network is reliable. The internet is not a reliable network, which means what? We need to find situations, or we need to find mechanisms to provide for some reliability in the network. Latency, another word for latency is what? Is the delay. I will review it to you in just a second. Delay, different types of components for delay. Latency is zero. No such thing as a latency zero. There will always be latency. Bandwidth, which is the capability of carrying traffic, is infinite. Is it infinite? No, it's not infinite. Clear? Network is secure. Of course, it's not secure. It's a public network, so it's not secure. Topology doesn't change. True or false? Again, it's false. Every time a node attaches to the network, every time a customer network attached to the internet, the topology has changed. So topology doesn't change. There is one administrator. I just told you that's, again, a false statement. The whole thing is divided into autonomous systems. Transport cost is zero. Again, no such thing. It takes some money to transport packets from one point to another point. Network is homogeneous. Again, it's a false statement. It consists of what? Multiple technologies. Some of them are wired, some of them are wireless. All of these things that we will study throughout the course. Okay, now what changed in the internet? The first thing, again, as I told you last time, is the traffic type. Now it's heavily oriented toward multimedia. Before, in the mid-70s, early 80s, it was basically electronic messaging and file transfers. Right now, it's all types of what? Multimedia. And what thing that determines one thing that these types of traffic require is a huge bandwidth. And that's the basic idea of the course. So the traffic types, multimedia, including audio, video, data, clips, images, and so on. So some of them are bursty, some of them are streamy. Let's see if you remember in a bursty traffic. This is again from 450 quickly, bursty traffic. Bursty traffic, this is the time axis. The data comes in what? In bursts, short bursts, and so on. Now in a bursty traffic, the peak rate, the peak data rate is much higher than the what? The average data rate. That's how you know that the traffic is what? Is bursty. That's how you know that the traffic is bursty. The peak data rate is much higher than the average data rate. Streamy traffic, the data rate or the traffic comes in what? In long, almost fixed or continuous bit rates streams like this. And in this case, the peak rate, average rate. The network, by the way, the routers in the network, do they prefer traffic like this or do they prefer traffic like this inside the network? Do they prefer this or do they prefer this type? They prefer this type, the streamy type traffic. This one is more predictable rather than this one. This one, for a short period of time, you might get a huge amount of traffic resulting in the queue, as I will show in just a second when you start reviewing the queuing theory. The queue starts building up for a very short period of time. So we will study sometimes, even if the traffic is bursty, the routers will try to shape it, to try to shape it. See, if you do have, for example, traffic shaping, so that you understand what I'm talking about. We'll talk about this later on in detail. I just brought it up for you to see the point. Traffic shape. Let's assume that you do have 50 kilobits per second traffic. 50 kilobits per second, let's 50 kilobits per second. Let's assume that we do have what? A file of 1 megabits. Now you can transmit this file at a rate of 1 megabits per second. How long will it take? How long will it take to transmit this file? If the file is 1 megabit, and if you are transmitting at a rate of 1 megabits per second, it will take what? It will take 1 second. In other words, you would do like this. This is the rate. This is the time. 0 to 1. And you are transmitting at a rate of what? 1 megabits per second. Clear? What if you transmit it at 10 megabits per second? What if you How long will it take? How long will it take? It will take, of course, it will take what? This T. It will take what? 0.1 second to transmit exactly the same file, and then what? The remaining 0.9 second. This is 1 second. The remaining 0.9 second is what? Nothing there, idle. Are you following? This is called what? Bursty traffic. This one is called what? Streamy traffic. You are transmitting at a what? Constant bit rate of what? 1 megabits per second, whereas this one is what? 10 megabits per second. Network prefer this type because it has somewhat predictability in it rather than what? Rather than in a bursty fashion for a short period of time, you are going to receive a large amount of traffic. We will see how the router will shape the traffic shortly. Okay. Now, all of these new services that we'll be talking about it in detail, including the multicast, including the voice over IP, the content deliveries, differentiated services, reservation, all of these types were not available in the original scheme of the internet. Remember, the original scheme of the internet, the service was basically the best effort. And here we will see how we can make reservation for resources and so on. Now, with this introduction of these new types of traffic, what resulted? More congestion, more delays, more losses, more failures. All of these are what? Are problems that we need to solve. And in addition, the conventional traffic models fail to capture reality properly. As when we will review of the queuing theory, we will see, or what you studied in 503, for example, most of the time the traffic is, the arrivals are represented by what? Or are modeled most of the time as a Poisson. With these types of traffic, the Poisson model might not be adequate. You need to go into more elaborate, more complicated models to capture the reality of these types of traffics. So all of these problems requires what? Requires solutions that we'll study throughout the semester. Now, one of the items that we'll study shortly, beginning next next week or the week after, is the quality of service. What is it? What is the quality of service? All of these traffic types, the new traffic types, require what? Different levels of quality of service. Quality of service is the ability of the network to provide the applications a level of performance needed for the application to function. For the application to function, the network needs to provide what? Certain levels of what? Certain levels of service. Those services or those levels is what is referred to as the quality of service. Now, how do we deal with this new traffic? The easy way. What is the easy way out? Easy way out means what? If you do have a problem and you want to solve it very quickly, what do? You just increase what? Increase the bandwidth. What results, by the way? When you increase the bandwidth, what results? The throughput, first of all, will go up. The delay will go what? Down. Why? Because if you remember, how do you calculate the transmission time? How do you calculate the transmission time of a packet? The transmission time of the packet is what? Is the length of the packet divided by what? Divided by the bit rate or divided by the bandwidth. So increasing the bandwidth results in what? The delay goes up. The delay goes down. But that's the easy way out. Easy way out means what? Any problem, you say what? Let's increase bandwidth. Let's increase bandwidth. Increasing the bandwidth results in what? More cost to the service provider. Clear? They need to make sure that their cost or they get their investment back. Clear? The return of investment. What is the other solution? Increases the buffer size. What would this one prevent? Or at least lower the possibility of what? The possibility that the router has to drop a packet. The longer the size of the buffer, the less chance the packets will what? Will be dropped. The delay will still what? Will still go up if the traffic is heavy, but the chances of the packet is dropped because there is no space in the buffer is what? Is going to be, is going to decrease. Clear? So increasing the buffer size, apply congestion control, traffic management, admission control, and so on and so forth. Currently, if you want to access the internet, currently, okay, do you need to make some kind of what? Arrangement with the network? Do you need to set up something? Clear? Nothing there. Regardless of whether the network is congested or not. With the new schemes of quality of service, the network needs to what? You need to take admission. Think about it this way. You need to take admission from the network to send your traffic. The network needs to figure out, are there resources in the network available to support what you are asking for? To support what you are asking for. If they do not have these resources, they would not allow you to enter the network. Because if you enter the network and the resources are not available, you are going to cause degradation of the performance to other users who are already what? Whose traffic is already in the network. So we are going to study all of these issues, situation, how to control the congestion, how to manage the traffic, the admission control, reservation, and so on and so forth. The question then, which is the big question, all of these mechanisms, are they going to work? Are they going to work? Most of them, by the way, most of them currently is only on a what? Is only on a piece of paper. Are you following me? They keep publishing standards and so on and so forth, specifications. The question is what? Are they going to be implemented? Are all of these mechanisms going to be implemented? Now we will see, for example, when we look at some of Cisco routers, for example, we will see that most of these mechanisms are actually what? Are actually embedded, are actually implemented in those routers, Okay, the question what is that you have to understand that the internet does not consist of only what? One company or one organization. There are several. So when we are talking about the quality of service end to end, that the traffic might go through multiple networks, clear through multiple networks. So we need to understand how that will work. It's a very complex network in scale, in interaction, in dynamics, several nodes, failure modes, including losses, crashes, loops, and so on. So we need to see some systematic way to deal with all of these issues. Now, again, you remember this from 450. Types of switching mechanism. This is a switch network. What is the opposite of a switch network as opposed to What is the other type? Shared, or what is referred to as a what? Broadcast network. A switch network, the traffic will go from one switch to another switch, a third switch, and a fourth switch, all the way to the what? All the way to the destination. We call it as what? A switched wide area network. A switch network does not need to be a what? A wide area network. We are familiar, for example, with a what? A LAN switch. You do have a switch like this. And the devices are connected to the switch here. This is A, for example, B, C, and D. A can communicate with B, and C can communicate with what? With D. This is a LAN switch. Clear? Okay. The broadcast or the shared network is like this. This is now a what? A hub. Or a what? A bus. In a hub, this one is going to be transmitting. This one is going to repeat it to all of them in here when it's transmitting. This one receive it, this one receive it, and so on. So. Now, keep in mind, when we say a shared network, does not mean that the end users is going to receive the traffic, every traffic. We are talking only on what? On the network interface card will receive the traffic. These are called shared networks. This is called switch networks. Okay. A switching type, again, you have seen all of this in 450. I don't know why am I reviewing this, just to refresh your memory. The first type of switching is called what? Packet switching, and another name for packet switching is what? Connectionless. One more time, what does connectionless mean? Connectionless means what? Means you are not going to establish a connection through the network. You are not going to establish a connection through a network. Connectionless packet switching, the packets are going what? Are going to be transmitted. No need to set up a connection. 1, 2, 3. Is there 1, 2, 3, 4? Is there a guarantee that the packets will receive in the same order? There is no guarantees that the packets will be received in the same order that they were transmitted. Every time the packet comes into the router will what? What is this, by the way? Based on what is known as what? Store and what? Forward. Store and forward. Every time the packet comes to a router, it will be stored, will be checked for errors, and it will then be what? Forwarded to the next node along the way. It receives. Whose responsibility is to put them back in order? It is the responsibility of the transport layer protocol, TCP for example, to put them back in the same order that they were transmitted. This is called connectionless protocol, and again, there is no guarantee for anything. No connection setup, no teardown phase. Each packet contains a destination address in the header. Packets traverse multiple hubs from source destination independent of each other. They may be received out of order. No guarantee of delivery, no guarantee of order delivery. If a router gets congested, the packets will be dropped, and so on. So, store and forward, when a packet arrives at a switch, or a router, it is stored in a queue until it gets forward. Now, when we get to the queuing in just a second, we will see that most of the time the router or the switch inside the router will have what? 2 sets of queues. One at the input and the other one is at what? At the output. We call it what? An IO queue, input queue and an output queue. And then it will what? It will, the router will process the header, which means what? It will check, first of all, check the header for errors, and it will what? It will parse the destination IP address, and then it will look into what? Into the routing table to determine what is the routing table lookup for the destination address. What mechanism do you use? The longest? Do you still remember this? Longest what? Prefix match. One of the technologies that we will study in this course shortly is called MPLS. MPLS stands for the multi-protocol multi-protocol label switching. Will avoid what? Will avoid going through this. We try to avoid going through what? Through this, these prefix matches and so on and so forth to reduce the delay. Queuing variations can result in what? In a random delay. This again, what we refer to as what? As the delay variation. Another name for delay variation is jitter. We'll speak on that in detail when we get to the quality of service. Packets, again, might overflow finite buffers and so on. So all of these things. Now, before we get to the virtual circuit, let's look at the timing diagram. You are all familiar with this. Again, you can see, you remember the chart from 450. In a timing diagram, you are going to be transmitting the packets as they... Huh? What happened? No hair. No hair. All gone. Gone due to age. Yeah, okay, good. Can you zoom in, please, a little bit? Thank you. Okay, this is packet switching. Again, you are going to be transmitting the packets as they are ready. This, for example, packet 1, packet 2, packet 3, and so on and so forth. And it is what? It is a store and forward. When this node receives the packet, it checks it out for errors and consult with the routing table, and then what? Forward it to the other node, and so on and so forth. The end-to-end delay, we did this calculation in 450, is from here to here. This is called the end-to-end delay. Okay, this is packet switching. Now, let's look at the second type of switching that we will be interested in this course. It's called what? Virtual circuit switching. Virtual circuit switching. Now, first of all, circuit switching, let's look at the timing of circuit switching one more time. In circuit switching, you are going to set up a circuit before you start transmitting your data. So this is what? This is the connection setup request. Connection setup request comes from the user to the service provider. And then what? You are going to set up a connection. In here, there is no, again, one more time, why there is no propagation delay here or queuing delay? I said no propagation delay, I'm sorry. No queuing delay or a processing delay because the circuit has already been what? Has already been set. Okay, once the circuit is set, so this one from here to here is the call setup time. Once the circuit is set up, you are going to start sending the traffic, and this one you need to tear it down. This is circuit switch. The problem with circuit switching is that the resources are going to be dedicated to the circuit for the duration of the call. If there is nothing to be transmitted, those resources are going to be what? Are going to be wasted. In virtual circuit switching, again, you are going to what? You are going to set up the virtual circuit. Again, you are going to set up the virtual circuit. However, the resources are not going to be what? Dedicated. They are still what? It is still based on a what? A store and forward situation. However, all the packets will follow, if you see this diagram, all the packets will follow the same route, 1, 2, 3, 1, 2, 3, 1, 2, 3, and so on and so forth. However, it's still, again, still this one, still a store and forward technology. An example of what? An example of the virtual circuit type is ATM, as we will see shortly. Clear? A virtual circuit, again, is not a dedicated path. This is not the same as circuit switching. Now, if we are going to use the beauty of using a virtual circuit is that in this case here, we really don't need an IP address to determine what is the next node. We only need a what? We only need some kind of an identifier. That identifier, we will refer to it as a what? As a label. Some kind of a what? A label or identifier. We will get to that again shortly. We all have taken this in 450. This is the difference between them. In virtual circuit model, typically wait a full RTT. RTT stands for what? Round trip time. Round trip time. Typically wait full RTT for the connection setup before sending the first data packet. While the connection request contains the full address of the destination, each data packet contains only a small identifier, making the per packet header overhead is very small. If a switch or a link in a connection fails, the connection is broken and a new one needs to be established. The other one, of course, is connectionless. Connection setup provides an opportunity to reserve the resources. I want you to understand that. What does this mean? While you are setting up the virtual connection, there is a chance for you to negotiate with the network to determine what? If you can reserve resources for the duration of the session. And again, we will see that shortly. In a datagram or connectionless, there is no what? There is no round trip delay waiting for the connection setup because there is no connection setup. By the way, the source host has no way of knowing if the network is capable of delivering a packet or if the destination host is even what? Up. Did you understand what that means? In a connectionless, you don't know whether the other side is what? Is up and ready to receive your packet. You don't know that. You just send your packets. In a virtual circuit, no, you know that the destination is what? The destination is up because destination has to accept the virtual circuit connection setup. Clear the request. Clear? So you would know that if the receiver is up or not. In datagram, all the packets are going to be retreated independently. It is possible to round around the failures and so on and so forth. Packet switching or connectionless is more flexible in that matter. Every packet needs to carry the full address rather than just an identifier, because the network is going to treat each packet separately. This is again the difference between what connection-oriented and or virtual circuit and connection-less. In a connectionless, the packet is coming in here. There is a destination address. This is the router. This is the switching mechanism. We will study, by the way, the architecture in detail, what goes inside the router and how we configure the router properly. So the packet will come in here, the routing table associated with it, and it will be forwarded to the next node. What do you notice, by the way, as far as the address is concerned? Did it change? Oh, it did not change. The address did not change. What is going to change is what? Going from one node to another node, which address is going to change? Which address is going to change? As your packet goes from one node to another node to a third node, which address is going to change? So what is going to change is the MAC address or the data link address. The IP address doesn't change. This is in case, by the way, in this case here, it will forward it here or here, depends on the other. In a virtual circuit, we have what? We have some kind of an identifier. This one, by the way, is much shorter than this one. And this one is just a lookup table. Whereas this one, you need to do the what? You need to do the longest prefix matching. This one is just a lookup table. Okay. So it comes in here and it will what? It will switch it to this side. And the switching is, this one does not need to make a what? A routing decision on a packet per packet basis. Once it sees this label, it knows that these are what? These packets are headed to this outgoing interface. So it will just send it here. Did you get the point? In here, the router has to make a routing decision on a packet per packet basis. In here, based on the label, the router will what? The switch inside the router will what? Switch the packet to the appropriate outgoing link. What do you see in here? In the table, what do you see? You see, if the label is this, then the outgoing interface is this. If the label is this, then the outgoing interface is this. Clear? Again, I will show you the details shortly on this one here. This is the timing diagram that, notice, by the way, is still a what? A store and forward. Whereas in circuit switching, there is no what? There is no processing or the queuing, because the circuit has already been what? Has already been established. Okay, now, then we studied, we reviewed this one last time, the multiplexing. Multiplexing means what? Is the process of aggregating traffic from several users. And again, as I told you, we do have two types of multiplexing, the statistical multiplexing and the synchronous multiplexing. This is time division multiplexing, not wavelength division multiplexing. In statistical multiplexing, again, the router takes advantage of what? The fact that not all of the sources are going to be active at the same time. So they will be what? They will be they will be overpopulated. Think about it this way. They will be oversized. So if the average arrival rate is less than the average service rate, you are going to what? You are going to use, the best way to use is to use what is known as a statistical multiplex. If the average service rate, no, this one is wrong. If the average service rate is what? Is less than, I'm sorry, less than. Correct this one. If the average service rate is less than the average arrival rate, the system becomes unstable, as I will show in just a second. So the first thing to do is to try to ensure that the system is what? Is stable. The cost, of course, increased buffering, increased queuing delays, and so on and so forth. If the traffic is smooth, i.e. the average rate is approximately equal to the peak rate, no need to play games with the capacity sizing. Use what? Synchronous TDM is better. Clear? Synchronous TDM is better if the average is the same as the what? Is the peak. Which means what? The time slots that are going to be lost is minimal. This is again, let's start reviewing. Let's start doing this. Okay, review of Q. I will also, by the way, set probably this Friday. I will talk with you about it at the end of the class to review the queuing from what? From EE 503. Let's see if you remember. Okay. Now, what are the elements of a queue? Elements or components of queue. What do we have? The first part is what is referred to as the population. What does population means? The traffic is generated from this population. This population could be what? Finite, or it could be what? Infinite. It could be finite population, or it could be infinite. Which one do you think is easier to model? Finite or infinite? Actually, infinite population is easier to model. Why? Can you tell me why? If it is a finite, then the arrival rate will depend on how many what? Will depend on how many packets are there in the system. Finite population is what? It's the number of packets or the number of users are what? Are finite. Clear? So the arrival rate is going to be limited on how many what? How many packets are there in the system, as I will show in just a second. It's much easier to design or to model the infinite model, use the infinite model. Then what do I have? I have the arrival process. Arrival process where the packets are going to be joining a what? A queue. This is the queue. And when we deal with the queue, we deal with what? Finite size, infinite size, and in here we do have the what? The waiting process. And then what is the other one? Is what are these? These are the servers. And again, here we do have what? A single, for example, a single server. Here we do have what? Multiple servers. This is the server time, service time. And then in addition, we also have what is known as the queuing discipline. Service policy. And the other one is what? Drop policy. What does the service policy mean? The order of the packets being what? Served. For example, an example of this is what? First come, first serve. That's what it's called the queuing discipline. A dropping policy is what? For example, last come, first drop. Are you last come, first drop? Why do I drop the last one that come? Because the queue has become what? It become full. Now, when we talk about the size of the queue is finite, this one is a what? It's a drop model. This one is a what? A drop or loss model. This one is a what? Delay model. Drop or loss model means what? Means when the queue reaches its capacity, it will what? It will drop the packets. In here, there is no what? There is no dropping. In here, there is no dropping. It just what? It just delay. Clear? Clear? Okay. The arrival process. Okay. The arrival process. Is usually modeled as anybody? 503 as Poisson. At an average rate of land packets per second, average rate of land packets per second. Do you remember the equation? The probability of, let's say, A of t, arrival, equal to what? K e to the what? Lambda t to the k over what? K factorial. K goes from 0, 1, 2, so. You remember this? Okay. Again, I will set up extra session to review all of these things for you. Okay. By the way, how does it look? This is the time. This is, for example, an arrival, another arrival here, a third arrival here, a fourth arrival here. These are the arrivals. What do I call this? This is tau 1. What is this? Tau 2. What is this? Tau 3. Okay, so what? Let tau be what? The arrival time. Arrival time. How do we model this? If arrival process is Poisson, arrival time is anybody? Exponential with PDF f tau of t equal anybody? Lambda e to the minus lambda t. T greater than or equal to 0. What is the average? What is the average? E stands for what? Expected value. Average arrival time is what? 1 over what? Land. 1 over land. Clear? Clear? No response. Oh. The service process. What is the property of a property of the exponential distribution is memoryless. What does that mean? Did you take this in 503? Is memory. What does it mean? When we say memoryless, what does it mean? Okay, when a packet, for example, when a packet arrives into a what? Into a router and see another packet being served, the remaining time to finish service does not depend on when the service has started. From the arriving packet of you, when you enter, for example, when you enter a bank and you see a customer being served, the time remaining for that customer to finish service does not depend on when he started service. From the point of view of the arriving customer. The arriving customer will say what? The service time is exponential, is still exponential. Clear? That's memoryless. Does not remember when it started. Service process, service time is also modeled as exponential, again, most of the time. S stands for what? Service, mu e to the minus mu t. T greater than or equal to 0. Where mu is what? Say that again. Average service. What? Average service what? Rate. 1 over mu is the what? Average service time. Clear? Again, we will put all of these ideas in just a second into perspective. Clear? Clear? Number of servers. Now, for a single server case, lambda, which is the what? Has to be less than what? Mu, which is the what? Average service rate. Clear? Otherwise, what will happen? Otherwise, what will happen? Q becomes what? Clear? Clear? That means what? It means this is again. This is the server, and this is the arrival. If lambda exceeds mu, the packets will begin to what? Will begin to pile up. Q becomes unstable, which means what? Delay goes to what? Infinity. Clear so far? Okay. Define role, which is called what? The server utilization factor as lambda over what? C mu, where C is the number of what? Servers. C is the number of servers. For a single server case, rho is equal to what? Lambda over what? Mu. Has to be less than 1. Or multiple servers, rho, which is lambda over C mu, has to be what? Less than 1. In a multiple server case, lambda over mu, does it have to be less than 1? Lambda over mu, not lambda over C mu. Lambda over mu, does it have to be less than 1? No, it does not have to be less than 1. But lambda over C mu has to be less than what? Has to be less than 1 for what? For the Q to be what? For the Q to be stable. All of this again, review from 503, a very quick review from 503. Okay, queuing discipline. First come, first serve. Last come, first serve. Random service. Priority service, and we'll talk about all of them shortly. All types of what? All types of queuing discipline. And here, by the way, we will also talk about what is known as WFQ. WFQ stands for what? Weighted fair queuing. We'll talk about this in detail shortly. All routers currently, all routers, especially Cisco routers, have what? Have a weighted fair queuing mechanism implemented in them. Clear so far? Clear so far? Okay. So this is the queue model that I just explained to you. This is the queue, the buffer. These are the arriving customers, the server, the departing customers, and so on. So to ensure stability, again, we need to reserve enough capacity so that the demand is less than the reserved capacity. Dynamically trying to detect overload and adapt either the demand or the capacity to resolve overload. The router will be able, by examining the queue, will be able to determine whether congestion will occur shortly or not. This is, again, as I told you, the traffic intensity, or what we refer to as utilization, is lambda I over R, as the A, by the way, is what? Lambda in this case is the average packet arrival rate. L is the packet length in bits per packet. So when we say, see this one R is measured in what? In bits per second. So in bits per second, this one is what? Average packet arrival rate in packets per what? Second. packets per second. I need to multiply by L, which is what the packet length in bits per packet. When you multiply packets per second by bits per second, bits per packet, the packet cancels and you end up with bits per second. And when it approaches 1, it means what? It means the queuing delay will approach what? Will approach infinity. That's again, this is for the single server case. If rho is equal to 0, the average queuing delay is what? Small. Why? Why? If the rho is very small, the average queuing delay is small, the amount of traffic offered into the network is what? Is very little. As rho approaches 1, the delay will go what? High. As it exceeds 1, then you are going to what? Then the traffic is going to exceed the amount, the capacity available, and you end up with the congestion. That's the instability. Okay, let's continue our review here. Let's take some examples. Single server. Queue. Okay, first of all, notation. N of T, the number of what? Number of packets in the system at time T, both waiting and being what? And being served. Both waiting and being served. This is a single server case. Okay, N, WT, and N, ST, number of packets being what? Oh, sorry, waiting. This one is a what? Is the number of packets being what? Served. Clear? Clear? How much is this value? It's a single server case. Is this a random variable? Do we know exactly it's 1? Could it be 0? Could it be 0? Could be 0. No packets is being what? No packets is being served. Notice, by the way, when there is no packets being served, will there be any queuing delay? There won't be any queuing delay. As soon as the packet comes, it will what? Start service. Clear? Oh, what is the relationship between these? N of T is equal to what? N W of T plus what? N S of T. When equilibrium or steady state is reached, the dependence on time is what? Is dropped. What does that mean? I write it like this. Did you get it or not? When equilibrium or the steady state has reached means what? I don't care at what time am I looking at the queue. At what time I'm looking at the queue. What is N will be? Verbally. What is N? N is the number of packets in the system, both waiting and being what? Served. You notice I did not say at time T, at any time. I don't care. The queue has reached what? Has reached the steady state. Why are we interested in the steady state? Any queue at the beginning. And let me ask a question. Any random experiment, when you begin performing it, at the beginning, there will be always what? Fluctuations. For example, tossing a coin. When you are tossing a coin, yes? Is it possible that the first 5 tosses you will get ahead? Yeah, which means what? Would you deduce that the probability of getting ahead is a 1? You don't say that. Why? Because at the beginning, you do have what? The random experiments will go through what? Through some transient behavior. It goes up and down, up and down, up and down. But over the long run, it will what? It will reach the equilibrium or the steady state. Clear? Okay. What is E of n? Is equal to what? E of NW plus what? E of NS. Clear? Clear? The expected value. Are each one of these random variables? Each one of them. Are they random variables? Each of them are what? A random variable. So we talk in terms of what? Expectation. We talk in terms of what? Distributions and so on and so forth. Clear? Clear? What kind of random variables are they? Are they discrete or are they continuous? They are discrete. All. Do we know their distribution or not yet? Not yet. This is not the arrival process. Do not confuse this. This is what? The total number of packets in the system, both waiting and being what? Being served. We need to figure out how is this one distributed. Clear? Okay. Now, the times, T, is the what? Total time spent in the system. T, both waiting and being what? Served. What is it equal to? What is the T equal to? W plus what? S. This is the what? Waiting time. This is the what? The service time. Clear? Okay. E of T is equal to what? E of W plus what? E of S. Clear so far? Clear so far? Okay. Every one of them. T, W, S. Every one of them. Are they random variables? They are random variables. Clear? They are random variables. Let me ask a question. What type of random variable is S? Discrete or continuous? The service time. Continuous. What type of random variable is W? Is it discrete or is it continuous? Or is it mixed? First of all, what is the meaning of the word continuous random variable? When you say this random variable is continuous, what does it mean? What does it mean when we say, this is not even 543, this is even before that. Aside. A random variable is said to be X, let's call it X, is said to be continuous if still waiting. Cannot hear you. Speak louder. We say a random variable X is continuous. What should I prove? It takes infinitely uncountable number of values. Yes? What does that mean? Mathematically, what does it mean? X is said to be continuous, i.e., it takes infinite number, infinitely uncountable number of values, such that Is exponential continuous? How about Gaussian? How about uniform? All of these are continuous, such that the probability that x takes on any specific value, is equal to what? 0. That's how you know that the random variable is what? Continuous. Why? Because there are how many values? Infinitely uncountable number of values. Yes? What is the probability that what? What is the probability of each individual value? If I tell you, for example, pick a number at random between 0 and 1. Pick a number at random between 0 and 1. How many numbers are there? Say that again. Infinitely uncountable. Yes? What is the probability that is equal to 0.5? 0. What is the probability that's equal to 0.4? 0. That does not mean that they will not happen. It just means that the probability that it will happen is infinitesimally small. Clear? Clear? What is if a random variable, x, is said to be discrete, if it takes what? Finite, or what? Infinitely, what? Countable. Means what? Integer. Countable number of values. Clear? Clear? It's what is mixed random variable. Mixed. From the definition, mixed is a random variable. A mixed random variable x is one that can take some discrete values in addition to continuous values. What does it mean? Continuous values. What does it mean? Listen to this thing. I tell you x can take values of what? 0, 1, 2, and anywhere between 3 and 4. How many values are there between 3 and 4? Infinitely uncountable number of values. But it also can take what? 0, 1, and 2. So 3 discrete components, and then what? Continuous component. Clear? Okay. Now let's get back to this. See if you can help me. These are times. All of them are times. Is S a continuous random variable? The service time. Service time is a continuous random variable. Clear? Clear? How about T, the total time that you spend in the system? Is it continuous? It's continuous. Are you following on? Why? Because this one is continuous. Clear? How about W? Is it continuous? The waiting time. It is continuous or not continuous? Or is it mixed? Remember, in a continuous random variable, the probability that the random variable takes on any specific value is equal to what? 0. The waiting time. A packet arrived into a router. He found the queue empty. He find a queue empty. What is the waiting time? 0. Which means what? Is it possible that is it possible a packet arrives at a router and sees the queue empty? It is possible. Are you following? Which means what? the probability of W equal to 0, W being what? The waiting time. The probability that W is equal to 0 is not equal to what? Does not equal to 0. Yes. Oh, okay. Thank you. Did you lose me? Did you lose me? You lost me. Did you lose me? You lost me. Concentrate. Concentrate. A packet, a continuous random variable is one that cannot take what? Any specific, the probability that x equal to small x, any specific value, the probability that x takes on that value is equal to what? 0. For any x. For any x. Clear? Waiting time. Notice, by the way, if the waiting time is 0, which means the queue is what? Empty when the packet arrives. When the packet arrives into the router, if W is equal to 0, what is T? T equal to S. Is S continuous? S is continuous. So T is what? It's continuous as well. Are you following me on that? If W is not equal to 0, which means what? There are packets ahead of the arriving packets already in the queue. Okay. Yes? Will this one also be continuous? This will also be continuous. Are you following me on that? Even if W is what? Is not equal to 0, this one is continuous. Why? Because this one is continuous. Clear? Okay. This continuous. This continuous. But is this continuous? This is not continuous. This is a mixed type. Why? Because there is a possibility that a packet will not what? Wait. What is the probability, by the way? For a single server case. For a single server case, what is the probability that the queue is empty? What is the probability that the queue is empty? The probability that queue is empty is the same as what? As the probability that the server is what? Idle. He is not doing anything. I'm not sure that you got to the point. In a single server. Okay, let me write it down. Okay, back. Queuing. Both T and S are what? Continuous random variables, but W is a mixed type. For the single server case. Remember, a single server case means how many servers? One, which means at most how many packets are there in the service facility, not in the queue, in the service facility. At most one, because it's a single server case. Yes? What is the probability that W is equal to 0? Verbally. First of all, verbally give it to me, and so that you understand how we approach it. What is the probability that W is equal to 0? Which means what? What is the probability that you are not going to wait? Who's you? Who's you? An arriving packet. An arriving packet. What is the probability that he will not wait? Is the probability that the server is what? Idle. Did you get this or not? Why? Because if the server is busy, an arriving packet has to what? Has to wait until the service is finished. Clear? But if the server is idle, are you going to wait? You are not going to wait. What is this equal to? That's equal to 1 minus rho. Rho is the what? Is the server utilization. Remember, rho is less than 1. Yes? So when we say row, is 1 minus row means what? The server is not being what? Utilized. Clear? Okay, good. We are out of time. Clear? Okay. Now, cut me off. Cut me off. Before you leave, I need to ask a question. Do you want me to set up review sessions on this? Huh? This not the cut me off, operator. Stop taping. Thank you, sir. Because some of you might not have taken this material. Need to make it clear to you is that the review sessions